Okay, as we were discussing in the previous video, so we are trying to find the voltage gain of this differential amplifier if the applied input voltage is differential in nature. So as it was mentioned in the previous video, differential input is one such input where the inputs V in 1 will not be same as V in 2. If you have two different input voltages at input 1, V in 1, V in 2, we call such type of input as differential input voltage. Now again in this differential input voltage, so let us assume that, let us name a differential input voltage as VID. So where I stands for the input voltage, let us assume that D is a differential. So let us give a suffix, give the naming of the input voltage. This is the voltage. I means this is like, okay, input. D means it is differential or different input. So now since I want to apply a different input voltage between V in 1 and V in 2, so what we'll do is, let us apply to V in 1 half of VID. Let us apply it as VID by 2. For V in 2, let us apply minus VID by 2. You can see we are applying two input voltages V in 1, V in 2, which are different. Can you see this is VID by 2, this is minus VID by 2. Since the magnitude of both the input voltages are same, the magnitudes may be same. Assume that this is some X volts and this is minus X volts. You can see the XX remains constant, but this is negative, this is out of phase. Since this is out of phase, I will say this is different from this. So what I'm applying is, I'm applying a single-ended input voltages, which is now VID by 2, and this is again a single-ended input voltage, it is minus VID by 2. Since the input voltage, of course this is still satisfied, you can see this is VID by 2, which is not equal to minus VID by 2. So this is a valid differential input, but applied single-endedly. So we are applying a single-ended input voltage to this, and we are applying a single-ended input voltage to this because one of the reference is ground. Since the input voltages are different, this is VID by 2 and this is minus VID by 2, I will say this is a differential input. Differential input applied to a differential amplifier. Now we are now applying a differential input to this particular signal. Let us try to understand, because of this small signal, what is the current that is going to flow here. Because we know that whenever you want to operate an operational amplifier, both the currents are required. That is, you need to have a DC current as well as the AC current. So we know that the DC current, which is ID1, ID2, which is flowing through the MOSFET. So what we are assuming is, we are assuming both the MOSFETs are identical and even the resistors are identical. We are assuming that half of the tail current will flow through both the MOSFETs. It is only half of the tail current that is flowing through both the MOSFETs. So because of this current, we are going to have a corresponding GM. So you can write GM is equal to under root of 2ID Kp W by L. So this is the expression where this ID happens to be I by 2. ID happens to be I by 2. Suppose if you want to find out what is GM1, you can write it as 2 times this ID will be actually I by 2. You can write it as this as I by 2. You can write it as Kp and W by L of first transistor, that is M1. Similarly, you can write it for GM2, which is equal to 2 I by 2, because ID is nothing but half of this one. Kp of, okay, this is of only NMOS transistor and this is W by L of 2. If of course we are assuming that W by L of 1 is equal to W by L of 2, so naturally this GM1 is equal to GM2, and of course we know that Kp of the MOSFETs will not be different whenever you consider a particular transistor. So these Kp's are different, I's are same, W by L of one transistor and W by L of second transistor we are assuming it to be same. So naturally GM1 becomes GM2. Let us call that transconductance resulting for these assumptions as GM. meaning this transistor has got a transconductance of GM due to the result of a current of capital I by 2, which is half of the tail current, the DC current that is flowing through the transistor. So now, of course, we all know that suppose if you want to write the small signal model of a particular transistor, this is how we write it. So this is, now you have a voltage controlled current source, which is now, suppose if you consider this is gate, drain and source, this is now VGS, and this is what, GM into VGS, assuming okay lambda equal to 0, where R0 will become infinite. R0 will become infinite. That's why I'm not writing any R0 here. Okay, this is the small signal representation of the MOSFET with the current. Suppose now I will say this as small signal current. Can I write the small signal current ID that is flowing into the drain of the MOSFET as equal to GM into VGS? Because this is the current magnitude, which is GM into VGS. So since we know that the small signal AC current that is flowing through the MOSFET over here, so this, suppose if I name it as small ID. So what is that small ID is equal to, it's actually GM into VGS in a general transistor, but for this particular differential amplifier, since the small signal applied is VID by 2, shall I name this ID as GM into VID by 2? So what I'll do is, for this particular transistor ID, for this particular circuit, can I write ID is equal to, ID as equal to, so what is this? So as we're writing here, it is GM into VID by 2, because whatever VGS I'm applying here is now VID. So before that, what we do is, let us try to write the AC equivalent model of this one, or the AC circuit of this one. So if you want to write the AC circuit, we know that we are supposed to make the voltage sources as ground, and then we need to make the current sources as open circuit. So let us write the actual circuit of differential amplifier and its AC equivalent. So let me start with the actual circuit. The actual circuit, what you have is this. So this is minus VSS, this is plus VDD, this is RD, this is again RD, this is VID by 2, of course, minus, this is NMOS, this is again NMOS, this is VID by 2, which is plus VID by 2. Okay, fine. Of course, this is V01, V02, we'll just not write it. So the AC equivalent of this, because now we want to write the AC equivalent. So first thing is that I should ground this. So let me ground this. We know that this current source will be made open circuit, and of course this is again grounded. Since it is open circuit, this ground has no meaning here. So I will again write, this is now VID by 2, this is minus VID by 2, because when I say only at this point, it is with respect to ground. This is again fine, this is RD, this is RD, this is V01, this is V02, this is NMOS, this is NMOS. Fine. So let us write, what is this? This is ID1. What is ID1 as per this? Shall we write ID1 is equal to GM1 into VID by 2. This is what is GM1 into VID by 2. Suppose if I write this, okay, now what I'll do, I will write, because now you can see, suppose if I write this as ID2, if I write this as ID2, so what is ID2 now? Is ID2 is exactly as in the previous case, is it not GM2 and the applied input voltage, since the applied input voltage is minus VID by 2, is this ID2, is it not equal to minus VID by 2? Just carefully note this. this negative sign is there because you have applied an input voltage which is negative. So to be very frank, ID1 is the current that is flowing in this direction, which is GM1 into VID by 2. The ID2 which is flowing in this direction is actually minus GM2 VID by 2. Suppose instead of writing ID2 like this, if I write this as ID2 dash. What is ID? Okay, I dash D2. This I dash D2, is it not equal to, because now what is I dash D2, is it not equal to minus of ID2? Because you can see I'm just reversing the direction of ID2 and I dash D2. So now I dash D2 is equal to minus of ID2, which is nothing but minus of minus means this will go off. It is GM2 VID by 2. If GM if GM1 is equal to GM2, can I write ID1 is equal to, of course, what is ID1? ID1 is actually GM into VID by 2. What is I dash D2 is actually GM into VID by 2. What I mean to say is, whatever current that comes over here, the same current will go here. Correct? Can you see the same current is flowing here? And the current that is flowing, I'm just talking about the AC current. The AC current that is flowing into this is actually zero. Actually zero. Even if you consider, okay, you can consider a resistor RSS across the current source. Even though if you have an RSS here, the AC current that would flow through this RSS would be zero in nature. So why this is zero means, because whatever current that flows through this particular transistor ID1, the same current will flow in the opposite direction in this M2 transistor, meaning whatever current that comes here, the same current goes here. The amount of AC current that is flowing through this particular network is actually zero. So what I mean to say is, we know that this is minus VSS and its AC equivalent is grounded here. Even though there is a resistor associated with this current source RSS, if you retain that, even making this open circuit, since there is no current flowing here, because why there is no current flowing to this particular RSS? Because this ID1 is equal to this I dash D2, because the magnitudes of the voltages are same and they are opposite in direction. Suppose if you are having 5 microampere of current going like this in top down, it is going from bottom up, it's again minus 5 microampere current. Meaning, even though you have an actual ground here, because of this input voltage of VID by 2 and minus VID by 2, you will still see a voltage of 0 volt here. Even though this is not actually grounded, this looks like a virtual ground. Why it is virtual ground? You can see this is virtual ground mainly because no current is flowing through this, because the drop here is 0. The drop here is 0 volt. Since this is 0, the current is not flowing through this, there is no drop here, the same voltage is retained here even though you are not physically connecting this. So that's why this particular terminal is called as virtual ground. This virtual ground will occur only when you are applying a differential input voltage over here, because the same current will flow in the opposite direction. This is what is phenomenon known as virtual ground in case of differential amplifiers. Now, okay, let us move on with the finding out what is V01 and V02. So now this is the current that is flowing through this. Okay, this is ID1. Same thing is flowing back here, which we named it as I dash D2. Because why we just named it as I dash D2? So that we have to have the opposite of this ID2 current. Suppose if I'm interested in knowing what is my output voltage V01, which is a single-ended voltage at this point with respect to ground. You can see this is the ground. So can I write V01 as equal to minus of ID1 into RD? Why it is minus of ID1 is because I'm interested in knowing what is this voltage plus minus here. This is my V01. So V01 is the voltage measured across RD with respect to ground. So let me consider a current which is going in the opposite direction, which is exactly minus of ID1. So that's why minus of ID1 multiplied by RD. But what is ID1? ID1 we know. So it is now minus of GM VID by 2 into RD is V01. So when I say this V01, V01 is a single-ended measured output voltage. So now I can write V01 by VID as equal to minus GM into RD by 2. Suppose if you write V01 divided by VID is equal to minus GM into RD by 2. So what is this V01? V01 is the voltage that is measured at this point with respect to ground divided by VID is given by minus GM into RD by 2. Similarly, if you find out what is V02, so let us also find out what is V02. Let us go with what is V02. So what is V02? It is again, now you can write it as I. So can I write it as I dash D2 into RD? This is I dash D2 into RD. You can see this is I dash, the current that is going in the opposite direction. But what is I dash D2? You can see it is now I dash D2 is GM into VID by 2 into RD. You can see there is no negative sign here. There is no negative sign here. But here for V01 we had minus of ID1 into RD. Why it was minus means because I was supposed to take this drop. Now since the current is flowing from this to this, so which is I dash D2, so I will retain the same expression for I dash D2, which is GM into VID by 2, which is this multiplied by RD. Suppose if you now find out what is V02 by VID, is it not equal to GM into RD by 2? Carefully notice this. If you apply VID by 2 and minus VID by 2, the voltage that you have measured at this point, suppose if you try to find the gain here, at this point, that is V01 by VID will be minus GM into RD by 2. Over here it is GM into RD by 2. You can see there is a plus sign, there is a negative sign. What I mean to say here is the single-ended voltage that is measured at this point is out of phase with VID, okay, because of this negative sign, because it is now, if you measure the output voltage at this V01 with respect to VID, it is out of phase. If you measure at V02, it is in phase. You can see there is no phase difference. Now let us try to find out what is plus and minus of this. What is the differential output voltage? So what we'll do is, so we actually measured two voltages, that is V01 and V02, which are nothing but the single-ended output voltages, which is nothing but so we wrote it as this was, okay, let me write it as VID and this is VID. So this was minus GM into RD by 2. This is GM into RD by 2. So I am interested in what is V01 by V02 by VID minus V01 by VID. So I want to measure a differential voltage. What is this V02 by VID? It's actually GM into RD by 2 minus of what is V01 by VID? it is minus of gm into rd by 2. If you actually subtract them, is it not becoming gm into rd by 2 plus gm into rd by 2, which happens to be gm rd by 2, and you can see this is plus, this is what is v02 minus v01 by vid. So v02 minus v01 divided by vid is gm into rd. So there is no rd by 2, sorry, there is no rd by 2, it is just gm into rd. So what we are trying to arrive at here is, if you are measuring a single-ended gain, it is minus gmrd by 2 at v01. If you are, for this minus indicates that it is out of phase. If you consider v02 and vid, you can see they are in phase. If at all, if you measure a differential voltage v02 minus v01 divided by vid, then this is, you can see this, the gain is actually twice. You have divided by 2, there is no divide by 2 here, so they are actually twice here. So maybe we'll just go to simulation and try to find out are they out of phase. You can see they are out of phase, they are actually in phase, and the differentially measured voltage will have a double the gain compared to the single-ended gain. And more than that, if you are measuring with respect to v02, if you are measuring with respect to v02 minus v01, it is in phase with the input voltage Vi. So that's what is, it is actually plus here, it's actually plus here. So we shall see all these things in the simulation. What we'll do is we'll just go to simulation. Hope I will get that particular, let me just see. Okay, let me just check it out. Otherwise we'll just try to have one such, we just have one transistor. Okay, let me have in MOSFET transistor 1 here, the other one I will, okay, this is the other transistor. Let me construct it. This is, okay, let me have a resistor of maybe, okay, 500 ohm. Let me have a copy of that. Let me put it over here. This is R2, this is fine, and let me connect those things, and let me have a power supply of maybe 0.9 volts and minus 0.9 volts, so that it will become 1.8. Let me take a power supply, okay, over here and one more here. Let me name it as okay, VDD over here, and this as VSS. Let me have this as VDD, and let me have one more as VSS. Okay, let me name this as VSS. Okay, let me rename it as VSS now. Let me have a tail current source. So this is my current source with a magnitude of some value. Let me just put it here. Okay. This is my current source. Let me construct the circuit now. Okay, let us pull down the current source. This is fine. Okay, let us take this down now. F7, let me put this, okay, connect it here. This is VSS. Let me connect the ground to this. Okay, let me have 0.9 here, 0.9, and this is minus 0.9 volts. We have done the connection. Let us have two more sources for your input voltage. So let me have an input voltage which is, let me have a copy of this, connect it here, and then you have a copy of this, connect it here. Let me change this to an input source. Let me not have the DC here. Let me have a sine source of amplitude around maybe 100 millivolt with a frequency of maybe 1 kilohertz. Okay, this is the sine wave. So let us have a similar type of signal over here. Now let us take a sine wave. Now let us have same 100 millivolt amplitude. Let the frequency be still 1k, but let us have a phase difference of 180 degrees, so that this corresponds to minus VID by 2. So VID by 2 is actually 100 millivolt. Of course, we are having same VID by 2 for both of them, but only thing is that we have just made it offset. We made that negative by putting a 180 degree phase shift. So let me have the grounds here. So let me connect. Now this is what is important. So we are applying two single-ended input voltages to V in 1 and V in 2, but they are out of phase. It's like, okay, VID by 2 and this is minus VID by 2 because you have a phase difference of 180 degree. Let me make the connections to this one. Okay, and then let me have again connection for this to this. Okay, this is done. Okay, now this is also done. And let me connect this to this. Let me have a current of okay, 1 milliampere. This is a current. Let us have a W by N of maybe, let us take a ratio of okay, let us have it as maybe the ratio can be 10. Okay, this is 100U, and let us have the same dimensions for this MOSFET also. This is 10U and then 100U. This is done. Suppose now everything is done now, so we are set with the things. So let us do dot OP and try to find out what is the current that is going, what is VGS and all those stuff. Let me have, okay, let me just name one terminal as V in 1. Let me say it as V in 1. Okay, this is V in 1, and of course let us try to find out what is the voltage VGS here. Let me run this. Okay, let me do dot OP. If you can actually see what is the voltages you have here, so you can see I have a current of how much. Suppose if you see, since we have put a tail current of 1 milliampere, let me just make sure that, okay, this is the tail current of 1 milliampere. Now ID1 and ID2 will be actually 0.5 milliampere, 0.5 milliampere. So that can be verified in this particular. If you can see here, this is this is through M2. You can see similarly through M1 it is half of the current. So this is 1 milliampere. Over here it is 0.5 milliampere and 0.5 milliampere, which is true here. And then of course you can able to measure what is the VGS and all those stuff. So let me just see, can I able to say this netlist. Okay, what I do is I just go to here you can make out. So you can see the VGS is actually 2.24 volts. So this is the amount of okay, let us just, oh sorry, okay, why I'm not getting it is I have not defined, I didn't put the model file, so that because of that I'm getting it as 2.24 volts, which is not possible here. The one initial thing, of course, one important that we have to do is we need to define the model file. Dot model NMOS, here it is KP is equal to 200U, comma VTO is equal to 0.4. I think this is enough for the first level. Okay, NMOS, I need to type it twice. This is MOS KP, fine. Now we just get it properly. Let me save this. Oh, sorry. Let me just save it in save as. Okay, let me just put it. Maybe put it on desktop. Let me have it as Diff amp 1, the schematic. Let me run now. If you can actually see now, of course the current is actually 0.5. Now if you go back to this, okay, view and then error log, now we can see the VGS. So VGS is actually 1.1 volt. So it's actually 1.1 volt, of course, which you can verify also. The VGS happens to be 1.1 volt, so which you can certainly verify it using this particular expression. So we have what I'll show you is, let me see, ID is equal to half kp W by L, of course, VGS minus VTO whole square. So from which I can able to write what is VGS is equal to VTO plus of under root of 2 ID kp W by L. So this way we can able to find out what is the required value of VGS, which I can able to find it for this particular case. So since this is 0.4 and plus of you have current is 0.5 milliampere divided by this is 200 micro and WL is 10. So if I substitute all those stuff, so it is 0.4 plus of under root of 1 exponential minus 3 divided by 200 exponential minus 6 into 10. If you can actually see, this happens to be 1.107 volt. So this is VGS. This is the value of VGS which we are supposed to get, because this is the ID in saturation condition, half into Kp W by L into VGS minus VTO whole square. From this you can able to get the expression for VGS, which is equal to VTO plus of, because this is after simple simplification, you will get VTO plus under root of 2 ID Kp into W by L. Because we know all these things, to get a current of 0.5 milliampere through the transistor, the required VGS is 1.10 volt, which will be derived by the circuit itself because of this supply. You can see this is 1.11 volt. So this is what we are looking at. This was supposed to be 1.107. So you almost have almost close to the expected value. So we are through with the current that is flowing here, and of course you can also find out what is GM. So as per this expression, GM is given by, so GM is supposed to be 2 ID Kp W by L. Suppose if you find out 2 into ID, so ID is actually 500 microampere. So you can write the GM value. GM value happens to be under root of 1 exponential minus 3 into Kp is 200 exponential minus, exponential minus 6 into W is 10. It's actually 1.41 millisiemens. So this is the value of GM that we can verify here also. Let me go to this view and then go to this error log. You can find the value of GM. Can you see here? This is GM value is 1.41, which is expected here. This is 1.41 millisiemens, which is exactly seen here. You can see it is 1.41 milli. So this is the value of GM. Since we know the value of GM, we can now predict the gain of the amplifier. So what is the single-ended gain, what is the differential gain, we can able to certainly find out what are those gains. So I'll just go back to this. We know that V01 by VID is equal to minus GM RD by 2, and then V02 by VID is plus GM RD by 2, and V02 minus V01 by VID. So these two are single-ended gains. So this is a differential gain. So this is actually GM into RD. So let us try to find out the values, because I know the value of RD as 500. So it is now 1.14. sorry 1.41 multiplied by okay 0.5. So now the gain is actually minus 0.705. Here the gain is plus 0.705. Of course into 2 would be 1.41. Actually the gain of the amplifier for this particular case is, it's actually, of course, even though we say it as gain, but since it is less than 1, you won't have an attenuation. Of course, we can certainly find, we can certainly increase the value of RD so that you'll get a gain more than 1 here. So let us see, can I able to make it equal to 1K? If I make it equal to 1K, if your MOSFET is still there in saturation region, I don't have issue. So let me make it 1K here. Let me again make it 1K. Then let me save it and run. If my current is 500, okay, this is 500. Okay, I think it is still in. Let me just go to this view and find out this. You can see this is still in saturation. If you can see this, VGS is 1.1 volt and VDS is 1.51. Can you see this VDS is more than VGS minus VTH? So since your VDS is 1.51, both the MOSFETs are in saturation region. So you may be just wondering, okay, what I'm trying to do. So I increase the value of RD, which was 500 ohm. I just made it equal to 1K. I want to reconfirm myself whether the increased value of RD is making my MOSFET to go to linear region or not. But it is not going to linear region. It is still there in saturation region. So since I have increased the value of RD by 500 to 1 kilo ohm, this gain becomes now minus 1.41. This will become plus 1.41 and this will become 2.82 volt per volt. So these are the gains now. So let us go back to this. Now let us do a transient analysis and try to see what is how does the waveforms looks like. So let me go to this, change this to transient, because I have applied a 1 kilohertz signal. Let us see it for maybe for 10 milliseconds so that you can see 10 cycles. Start from 0 and then go with 1 microsecond step. Let me run it. Now let me see the input voltage. This is I will say this is V in 1. You can see V in 2 is exactly opposite. You can see, let me just change the color of this. V in 2 is actually just the opposite because we applied minus VID by 2. So let us what I'll do is, let me just delete for the time being over here. Now I want to see what is the voltage here. So let me name this as V01. V01 is this over here, and let me name this as V02 so that you can able to find out what is the. Now I will connect this to this, and I will connect this to this. I will just have a look at the polarity of this one. Now this is V in 1. This is actually VID by 2. This is now V01. If you can actually see this V01 is actually out of phase with the input voltage. You can see this is input voltage, green one. If you can see, if the input is rising, the output is actually dropping down. So output is actually dropping down. So what does this dropping down means is, since it is dropping means it is actually out of phase. So that's what we saw here. So what we saw here is, the voltage that you are measuring at this point is always out of phase with the input voltage, which is VID by 2. So that's what you are seeing here. You can see this is actually out of phase. Suppose if you see the other output voltage, that is V02. Suppose if you see V02 over here, it will be actually in phase with this. See here, this red one, is it not in phase with the green one? Because green one is VID by 2. VID by 2. You can see this is the V02 is actually in phase with VID, whereas the blue one, which is V01, you can see the blue one. Let me just change it to a different color. I'll make this. You can see this is V01, this is actually out of phase. Now if I measure the differential voltage, so this is what is, of course we'll just find the gain maybe in the next video. We'll actually verify what is the gain, or we'll just do it now. What is this? This is actually V in 1, which is actually VID by 2. So since VID by 2 is 100 millivolt, so then what is VID? So VID is naturally equal to, let me just go here, VID by 2 peak is 100 millivolt. So naturally VID happens to be 200 millivolt. Then what is V naught 1? So let us see what is V naught 1 magnitude peak voltage. I'm just measuring the peak. So this was measured as peak. Let me go back to this and measure. So let me just measure. What I'll do is I'll just take one more plane and I'll take only V naught 1 here. Let me just measure the peak voltage, that is from here to, because I want to take this as my reference. If you can actually see there, this is this peak to this peak, from this reference to this voltage. Can you see the difference is, the vertical difference is 139. This actually, since I'm looking at, okay, let us simply measure the peak to peak voltage. So it would be better to measure the peak to peak voltage. So V naught 1 peak to peak is, so let me write what is V naught 1 peak to peak is. You can see it is almost 280 millivolt. 280 millivolt. Forget about that negative. So what is VID by 2 peak to peak is actually 200 millivolt. What is VID peak to peak then? This will be 400 millivolt. 400 millivolt. Let me just go back here and then try to find out. Okay. Okay, this is what we have now. Okay, let us find out what is the gain of this amplifier.